Today we're going to talk about our final gas law, PV equals nRT. Now up until now we have not included the amount of moles in any of our equations. So if you look at this, you're going to recognize some things that we've been working with and talking about for the last two chapters. Here's P for pressure, here's V for volume, there's T for temperature. We know when they're all together, we have the combined gas law. So what is N? Well, N stands for number of moles. And R stands for the gas constant. Now, if you looked up the gas constant in a number of tables, you would see that there are multiple values of it. Why is that? I'm going to teach you the two main values for the gas constant, and I'm going to show you where they come from so it's not some sort of mystery like it was to me when I was in school. I was like, oh, there's an R and I have to memorize this value. Let me show you where it comes from. If I take this equation, my ideal gas law, and I want to solve for R, I divide both sides by NT, right? Math. Now I can say PV over NT equals R. So let's calculate R for standard conditions if I have kilopascals. If I have standard conditions and I have kilopascals, P is going to be 101.3 kilopascals. I'll put V in a minute. If I have 1 mole, then my volume has to be 22.4 liters. And it's at standard conditions, so my temperature has to be 273. Oh, let's put Kelvin in there. Kelvin. Okay, so I'm going to pause the video or wait 5 seconds so you can pause the video, and I want you to solve for this. Solve for all those numbers. When you solve for them, you should get 8.314. Well, what are the units? kPa times liters over mole times Kelvin. Or you could say 8.314 liters times kPa over Kelvin moles. It doesn't matter. So this is the R value that we use when we have liters, kilopascals, kelvins, and mole. But a lot of times we do these problems when we have atmospheres. So let's calculate, using the same formula up here, let's calculate R when we have atmospheres. Well, what is standard pressure in atmospheres? Standard pressure in atmospheres is 1. Remember, I'm using this equation again, and I'm solving for my R value when I have atmospheres. So for P, I'm going to put in 1. I'm going to have 1 mole again. My temperature is going to be standard, 273 Kelvin. And since I have 1 mole, I have 22.4 liters. So once again, I'm going to wait 5 seconds. And you pause the video, and you go ahead and solve for R with these numbers. And when you solve for R with these numbers, you should get 0.0821. What are my units? Atmospheres times liters over mole Kelvin. There's my second R value. So you're provided these R values. You just have to know when to use them. You're going to use the 8.3141 when you're provided your pressure in kilopascals, and you're going to use your 0.0821 when you're provided the pressure in atmospheres. R is called your gas constant. Let's take the ideal gas law now and apply it to this problem. I got this problem from the Pearson Chemistry Foundation edition book on page 442, and I modified it slightly. It says right here at 34 degrees Celsius, so there's our temperature. The pressure inside a nitrogen-filled balloon, tennis ball, is 212. The volume of the tennis ball is 0.148. How many moles of nitrogen gas are in the tennis ball? How many grams of nitrogen gas are in the tennis ball? Okay, so I have 34 degrees Celsius as my temperature. I know I can't use degrees C, so I'm going to add 273. And when I add 273, I get 307 Kelvin. And then for my P, for my pressure, I have 212 kPa. That means for my R, I've got to use the 8.314 R value because I have my pressure in kilopascals. Okay, so let's plug and chug out this answer. So here we go, 212. Volume is 0.148. Number of moles is what we're solving for. R value for this pressure is 8.314, and the temperature is 307. So now we're going to go through and we're going to solve for N. When you solve for N, I'm going to wait 5 seconds so you can pause the video and do this yourself. You should get 0.0123 moles. Now that's not in correct scientific notation. We do have the correct number of sig figs though, because there was 3, that's a definition, so ignore it, and 3. So we have 3 in our answer, but remember in scientific notation you want a number, a decimal, all your other numbers, times 10 to the -2 moles of nitrogen. Now we know that nitrogen is diatomic, so now I want to convert from moles of nitrogen to grams of nitrogen. And when you remember from chapter 10 or from our mole chapter, when you go from moles to grams, you get the molar mass from the periodic table. Well, the molar mass for nitrogen is 14, so for N2 it's 14 times 2, which is 28 grams. And then all you do is multiply, because our dimensional analysis setup tells us that. And I'll pause for 5 seconds while you pause and do this yourself. And you should get 0.344 grams of nitrogen. So that's how many grams of nitrogen are in the tennis ball. There are 0.0123 moles of nitrogen in the tennis ball. How did we solve it? We used the ideal gas law, solving for N, our number of moles. How did we know to use an R value of 8.314? This is the R value that goes with kilopascals. So another great example of science working for us and plugging and chugging into the correct formula.